Hello everyone, welcome to our talk, The Road to Private Methods, brought to you by myself, Titian Cernicova-Dragomir, and my colleague Kubilay Kahveci. We are both engineers within Bloomberg in the JavaScript infrastructure team, where we deliver tooling for Bloomberg developers that use JavaScript. And earlier this year, we submitted a pull request to TypeScript that implemented private methods and accessors in TypeScript. First, let's see what we'll cover today. We'll talk about exactly what private class elements are. We're going to see exactly what we contributed to the TypeScript compiler. And we're going to talk about how we downlevel private class elements. So what exactly was our contribution? Well, the pull request, which was merged for TypeScript 4.3, it was a pretty big pull request. We're pretty proud of it. Implemented the ECMAScript specification for private class elements. Now, some of you may already be familiar with private class fields, and you might be thinking, what does this add? The answer is it adds private instance methods, it adds private instance accessors, and it adds private static members altogether. Let's first of all see exactly what private class elements are. I want to make clear that this is not a TypeScript feature. This is actually part of the JavaScript standard now. And what this pull request did was allow us to use this new feature in the TypeScript language. To understand private instance class elements, we can look at them in comparison to their public counterparts. At the very basic level, they look very similar, but they are named with a hashtag prefix. So basically, if you rename all of your fields, your accessors, and your methods with this hashtag prefix, things will work mostly the same inside the class. The difference is when you try to access these private members from outside of the class, you will get an error. And I want to point out that this is not just a TypeScript error. This isn't the same as the error you got when you used the private modifier. No, this is going to be a runtime error. This is something that the runtime is going to issue if you actually try to access these fields. The thing that we want to take away from this slide is the fact that these private members are actually scoped to the class that they're declared in. So if you actually try to access them outside of the class, this is actually a syntactic error because these are not defined in that scope. Another restriction is that these members are only accessible on instances of the class that declared them. So for example, if you have a person class and you have an animal class, and these two are in no way related, and they both declared the display age private member, well, we will be able to access person.displayAge, but we won't be able to access animal.displayAge. Right? Even though these two share a name, you cannot access them because they are declared in different classes, and each one of them is a different private identifier, even though they share a name. They are, however, accessible on instances of derived classes, but the restriction again applies that they're only accessible in the class that declared the private member to begin with. So for example, if we have a person class that has a display age private member, and we have a doctor class that inherits from person, we can access doctor.displayAge within the person class. That works. However, we cannot access doctor.displayAge from inside the doctor class because displayAge was not declared inside the doctor class. It was declared in the person class. What about the static side of things? Well, again, we can understand them by comparison to their public counterparts. Again, the difference we see first is the fact that they are named with a hashtag prefix. And if we rename our members, our accessors, our methods with this hashtag prefix, inside the class, things will work mostly the same. Again, the difference is that these private identifiers are only accessible from the scope of the class that declared them. So if you try to access person.initialize from outside the class, this won't actually work. A difference with public static members is that they're not accessible on anything except the class that declared them. So for example, if we have a doctor class that extends a person, for public members, for public static members, we would expect that we can access doctor.initialize. But this is not the case for static ones. We cannot access the initialize static private method on doctor. We can only access it on person, the class that actually declared it. So let's see how exactly we got this feature. How did it go from idea to implementation? The first commit to the repository that holds the spec was all the way back in 2015. And the specification got through the stages of standardization. It reached stage 3 in 2017, and it reached stage 4, the final stage of standardization, earlier this year. What happened between stage 3 and stage 4? The answer is implementation happened. And we start out with Babel, which implemented part of the specification in several releases. And these were done in a collaboration between engineers here in Bloomberg and the maintainers of the Babel project. Until in September 2019, we got the whole spec implemented. What about runtimes? Well, V8 implemented private fields in 2019 and private methods in 2020. Safari had a similar approach, implementing private fields in 2020 and private methods in 2021. Firefox implemented the whole spec in one go, and it released it earlier this year. So what about TypeScript? Well, TypeScript got private fields last year in 2020, and some of you might be familiar with the talk at last year's TSConf given by my colleague Joey Watts about his contribution to the TypeScript compiler that implemented private fields. And private methods arrived earlier this year through the contribution that myself and my colleague Kubilay made to the TypeScript compiler. So let's take a look at this contribution. Like we said, it was a pretty big contribution, 370 files changed, 50,000 lines of code added. Let's see how this fits into the TypeScript compiler. As you may know, the TypeScript compiler has several phases: the scanner, which splits up the input string into tokens, the parser, which creates the abstract syntax trees, the binder, which builds symbol tables, the checker, which ensures that the TypeScript type system rules are followed, and the emitter, which takes TypeScript and emits JavaScript code. Now, we didn't actually have to do any changes in the first 3 parts of the compiler, mostly because the changes that we needed were already there from the implementation of private fields. We did make some changes in the checker and some changes in the emitter. And you might notice that the numbers don't really add up. The reason is that most of the rest of the code is actually in tests. This was a pretty big feature. Lots of new types of members were added, and we wanted to make sure that everything works as expected. And let's look at some of the changes we made in the checker. The first type of change that we needed to make was to remove some errors. For example, previously, methods could not be named with a private identifier. Now they can. So we just removed some code. We deleted the code, the error went away. Similarly, accessors could not be named with a private identifier. This is no longer the case, so again, we had to delete some code. Static modifier cannot be used with a private identifier. Well, now it can. So again, we just removed some code. Another type of change that we had to make was to actually add errors for known limitations. And one such example would be for decorators, which are used in conjunction with static private members. The decorators that are part of TypeScript are actually not on a path to standardization. And when we tried to emit JavaScript code that had both a decorator and a static private field, we discovered that there was no clear way to do this. And rather than implement something which was not spec compliant and which likely would never be spec compliant, we decided to just error out on this case and wait for the spec to catch up and before we actually implement anything. This change was also not particularly complicated. We just took the class node. We saw if it had decorators, if it also had members that were static and private, then we issue this error. Another change that we made was to actually improve spelling suggestions. Previously, if you were in a context where a private field was not accessible, TypeScript would still suggest that private field as a spelling suggestion. This is no longer the case. This actually also applies to private and protected modifiers as well, which were already in TypeScript. This change was a bit more complicated. The basic idea is that we take the members of the type and we filter them based on the accessibility at the particular at the given context. The last change I want to talk about is the check for duplicate fields. Now you might be wondering, weren't duplicate fields already an error? And the answer is yes, they were. And as long as you have instance duplication, for example, you have two instance members that have the same name or two static members that have the same name, this already worked mostly. However, the difference is that the specification for private class members states that you cannot have a static member and an instance member that have the same name. Why is this? Well, the answer is that since these identifiers are scoped to the class, when the runtime has to look up a particular identifier, it will look to the class in which it is in. So if you have both a static and an instance member with the same identifier, this will be ambiguous. It won't be clear which one you're trying to refer to. So the spec makes this an explicit error. Now, the reason this was a bit more complicated is that some of the checks for duplication happen in the binder and others happen in the checker. We chose to make most of these errors, most of these checks happen in the checker. And it was actually a bit more complicated. This is just part of the code. And it also resulted in us writing a pretty big test, which checks for all possible combinations. We wanted to make sure that we got this just right. You have to take into account that some duplication is actually okay. For example, if you have a get accessor and a set accessor with the same name and they're both static or they're both instance, that's fine. But for example, if you were to have a static get accessor and an instance set accessor with the same name, that's actually no longer okay. It's not an okay kind of duplication. So we had to write the test that was actually pretty large and took into account all possible combinations. I'd like to hand it over now to my colleague Kubi to explain to us exactly how we dealt with the JavaScript emit part of this.
Thank you, Titian. Yeah, in this part of the talk, we will be talking through how private methods appear in the JavaScript output that's generated by TypeScript. So TypeScript can downlevel certain JavaScript features if you target an older version of the language. And that can be done using the target compiler option in tsconfig. And it's very common for projects that need to support older runtimes to use this feature, such as web projects that usually need to run on a range of different browsers and versions. So to support this, we need to implement hash private semantics without using the hash symbol, because that's not a valid syntax in the older versions of the language. In doing so, we definitely aim for semantic correctness. So we would like to achieve hard privacy at runtime. We want the generated code to be optimized in terms of memory because this is going to be production code. Readability is definitely important to us, especially for debugging situations where you might not have access to the source code or to source maps. And we also would like to pay attention to backwards compatibility with tslib, which is a separate package that contains some helper functions that are used by the compiler in the emitted JavaScript. So there are two fundamental rules on semantics that we need to pay attention here in the JavaScript emit. First, as Titian showed in the examples, private names are only accessible in the lexical scope of the declaring class. If this is not the case, then it's a syntax error. Since private names has to be declared statically and cannot be added dynamically to a class, this can be determined only by traversing the abstract syntax tree of the code. Whenever you enter a class definition, you will have a list of valid private names in that scope. So these errors are ideally handled in the checker, but because of an implementation detail in the compiler, you might end up with invalid syntax in the emitter. And if we see that, we just let that through so that the output stays invalid as well. The second rule is the access to private members has to be through the defining class for the static part of the class or through the branded instances of the class for the instance members on the class. Just because how dynamic JavaScript is, this is not always statically analyzable. So it requires some runtime code to be injected. For the static part of the class, we need to keep track of the defining class. And there can only be one class that defines the static members. And we can store that inside a variable, and then we can do a reference check later for branch checking. For the instance members, though, we need to keep track of all of the branded instances of the class that's created. So we could potentially store them in an array, and then we can look if the particular instance is in the array that is trying to access a private member, or we could put them into a set to optimize the lookup time. And those would potentially work, but they would come with a major cost on memory. Since the instances of a class can go out of scope, most of the JavaScript engines will just destroy them to free up some memory. And if we were to keep references to those objects inside an array or a set, we would be preventing the garbage collection of those objects. And that's where a weak set comes in handy. It works very similar to a set, except the references it holds are not strong references, so they do not prevent garbage collection. So let's look at some examples here. We have a simple hello world class here with two static methods. One of them is public, the other one is private. The public hello method calls the private decorate method, and that adds some emojis to a string. Let's run this through the compiler, and we will see an output like this. I don't expect you to read the code here. We will be focusing on smaller parts in a minute, but we can see there is a helper function added at the top, and class body has changed a bit. And then there are some variables that we added towards the bottom. Let's look at those variables first. So first, we created a variable to keep a reference to the class. This will be used later for branch checking. And we also removed the private method from the class body so that it's not accessible publicly, and it is stored as a free function in the module. And then let's look at the helper function we added at the top. So this helper function basically gates the access to the private method. It takes 3 arguments. Receiver is the object you use to access the private member on. State is the state we keep for branch checking. In this particular case, it's a reference to the class. And F is the private method that we are trying to access here. So we do a reference check to compare receiver and the state. If they're not equal, that means you're not allowed to access this private member. So we throw a type error. This is what we call the branch checking. If that succeeds, then you're free to use the private method. So we return the private method to the caller. And on the usage side, our hello world.hashDecorate call is replaced with a call to this helper. And this helper will give us back to private method, and then we can call that private method with the correct this and arguments. So let's see how we can support instance methods in a similar way. We have the same example here, except the methods are not static this time. They are instance methods. So we run this through the compiler, and we get this output. Again, we have some variables added at the bottom. So we still have the private method removed from the class body, and it is stored as a free function. And then we also created an hello world instances variable that's initialized as a weak set. This is where we will store the instances of this class. And to do that, we added a constructor to the class. Every time a new instance is created, we add that instance to the weak set. So this is how we populate the weak set. And then there were some changes to the helper function. So state argument of the helper function just became polymorphic. If it's a type of function, which means it's a class and we are on the static side of things, we still have our reference check. If it's not, we assume it's a weak set. So we use the has method to look up whether the receiver is inside the set or not. This is our branch check for the instance part of the class. If that fails, we again throw the same type error. If that succeeds, we give access to the private method. And then on the usage side, similarly, our this.hashDecorate call is replaced with a call to the helper function. And helper function returns the private method, and then we call the private method with the correct arguments. And finally, I also want to show how private accessors can be supported in a similar way. We have the Hello World class again. This time our private member is a getter, and we call this private getter from the public hello function. We run this through the compiler, and we get this output. So let's focus on the highlighted bits that is different to the private methods. So our helper function gained a kind parameter now. We have the same branch check, and then if the branch check succeeds, we look at the kind parameter. If we are using an accessor, instead of returning the function, we call the function and return the result. If that's not the case, we assume it's a method and we just return the method itself. Similarly, on the usage side, our this.hash message expression is replaced with a call to the helper function. This time we also pass a kind argument to indicate that we are trying to use an accessor here. So examples we have seen today only show the read operations from private members. Obviously, assignments and updates are possible, for example, using a private setter, and those are done using a different helper function called class private field set. It works in a very similar way. It first does the branch check to see if you're allowed to access that private member, and then if that succeeds, it does the operation to update or assign new values. We also support private instance fields and private static fields, and those are essentially a different kind in those helper functions. And also there are some custom runtime error messages that's defined by the spec in certain cases. For example, if you have a private setter without a private getter or vice versa, or if you try to update a method or an accessor which are not writable, there needs to be certain runtime errors raised. And considering all of that, the full implementation of these functions is a little more complicated than what is shown here. But if you're interested in the details of it, please check out this link after the presentation. So as part of this work, we have been looking at implementations of this feature in different engines or in other transpilers for inspiration. And as it can happen in any software, we discovered some issues. There were tiny spec compliance issues in Babel, and they're all fixed now, so that's great. We also identified a crash in V8 when using a compound assignment to a private setter. So in this example, we have a private getter and a setter named hash foo, and plus equals sign is the compound operator, is the compound assignment here. And this used to crash in V8's bytecode generator. This was interesting because it's not your code that's failing, it's the JavaScript engine crashing, which is probably the last thing they would want. They actually have fuzz testing in V8 to generate random syntax to try to crash the engine, and it wasn't caught, this syntax wasn't caught in there. But as always, V8 team has been very responsive to the issue, and they basically fixed it in less than a day. Before we finish, we really have to thank the TypeScript team for their support throughout our contributions, specifically Ron Buckton, who has provided incredibly helpful reviews during our contribution. It was really fun working with them, as always. And we also would like to extend our thanks to the Bloomberg folks who worked on these features before. As Titian showed on the timeline, Babel had all of the class features before TypeScript that was contributed by Tim McClure and Robin Ricard, and together with the Babel team, and their implementation was massively useful as an inspiration to us. Joey Watts, Max Hyber, together with Michael, Jaideep, and Rob, they contributed private fields implementation to TypeScript last year, and they built a lot of the infrastructure that we use in private methods implementation. Also, Joey Watts here at TSConf gave a talk about their contribution last year. I would definitely recommend checking that out if you haven't seen it yet. So this was the story of our contribution to TypeScript. Some of you might be wondering if it's time to celebrate yet. And to that, I would say yes. As we have seen in the timeline earlier, all of the major browsers shipped the feature. Node LTS versions support the feature. TypeScript supported. Babel has it. In most of the development and build tools also gaining support for it. So please go ahead and start using it. And thank you very much for joining us today.